Welcome back. In the first part of this lecture, we introduced the idea that light, everything we can see into visible light, as well as radio all the way up to gamma rays, can be thought of as electromagnetic radiation in the form of electromagnetic waves, changing electric and magnetic fields propagating along at the speed of light. We showed how electromagnetic waves have many of the similar properties to water waves and sound waves, and introduced the ideas of wavelength and frequency and amplitude of light. Light carries energy, and one of the interesting things about light carrying energy is that this tells us that light can also be described in a very different way as individual particles. Albert Einstein, in the early 20th century, explained the photoelectric effect by saying that light consists of tiny particles. The photoelectric effect was observed in the laboratory that when one bombarded a piece of metal, for example potassium or cesium, with different wavelengths of light, electrons would be kicked out of the metal, which could then be detected as causing a little bit of an electric charge. But it was noticed early on that while colors of light like blue light and green light in some metals could produce copious electrons, red light shining on the metal would produce no light at all. And it didn't matter how brightly the red light shone. It could be faint, it could be booming. No electrons would come off. But if you shone purple light or green light on the metal, light would come off, electrons would come off one after the other. So something was going on. There was something about the metal that knew something about the color of the light. But it didn't matter how much light was falling, except to give, if there was no electrons coming off, didn't matter whether you hit it with a lot of light or little, there were no electrons coming. But once you got above to a certain color, usually bluer, towards green and blue and purple, then all of a sudden electrons would just pour off proportional to the brightness of the light that was hitting it. This was called the photoelectric effect. It cannot be understood easily in terms of electromagnetic waves, but Einstein realized you could understand it if instead of viewing light as electromagnetic waves, you understood light as little tiny packets of energy. Red light having less energy than blue light, and that there was a threshold involved, that only a light particle above a certain energy had enough energy to kick an electron free from the atoms in the metal. And therefore you could view light as a series of small particles. Physicist Max Planck gave these particles the name photons. It's interesting to note that the work on the photoelectric effect was what Einstein was awarded the 1922 Nobel Prize in Physics for, not his much more famous and in many ways more far-reaching work on relativity and the theory of gravity. The energy of a photon is related to the frequency of the equivalent wave, and is given by this formula that the energy of a photon is equal to a constant h times the frequency. H is called Planck's constant, named in honor of German physicist Max Planck, who first coined the term photon and did seminal studies in electromagnetic radiation and the particle nature of light in the early 20th century. A light bulb produces a great number of photons. If we add up all the photons that come off of a typical 60-watt light bulb, we would find that there are 25 billion photons per second coming up off this light bulb. The photon picture of light is actually very convenient from the point of view of being able to quantify the amount of light coming off of a source, what we call usually the brightness. Whereas talking about waves and wave amplitude is actually not a very good way to describe how bright a source of light is. What is it? Is light a wave or is light a particle? The answer is, actually it's both. And this is because light is a quantum phenomenon, and we have to deal with the world of quantum strangeness. The quantum world occurs in the realm of the very small or at very high energies, a world that we normally don't live in, but we interact with all the time. Light is both a particle and a wave. It is technically an entity called a quantum. It is a carrier, a unit carrier of energy. I can equally describe it as an electromagnetic wave or as a photon. Which description works best? Both and neither. I know, this is starting to sound like one of those Zen haiku koan things, but really, this is actually a proper way of looking at it. Sometimes it's very convenient to treat light as electromagnetic waves. For example, when talking about radio waves, and we talk about the wavelength of a light telling us the size of an antenna or the frequency of the waves that are coming to us. Other times it's convenient to talk about photons when we're talking about brightness. We're talking about how much energy each photon carries, how many photons are coming of what distribution of energies. So we're going to be interchanging back and forth between talking about wavelength, talking about frequencies, talking about photon energies. And while it may seem counterintuitive to talk about the wavelength of a photon or the frequency of a photon, bear in mind, fundamentally we're talking about the energy of a photon that has an equivalent frequency or wavelength when viewed in the wave picture of light. And indeed, what is the speed of a photon? It's that same speed of light we saw for the speed of an electromagnetic wave. Light comes in many different energies, many different frequencies and wavelengths of light. And we often talk about this distribution of all these different wavelengths, or when talking about visible light, all the different colors and energies of light as the spectrum of the light. We usually describe spectra, or at least I usually describe spectra, because I work in visible and infrared wavelengths, as in terms of the wavelengths of the light, as going from short wavelengths to long wavelengths. In this picture, we have a classic picture of white light entering a glass prism and being broken into its rainbow of component colors. From very short wavelength light, 400 nanometers at the far blue, up to very long wavelength light, red light, up at about 700 nanometers. You can remember the approximate order of the colors of the spectrum using a simple mnemonic developed by artists Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet, with wavelengths running from long wavelength, about 700 nanometers, for the reddest wavelength of light that the human eye can see on average, to green light, which is about 550 nanometers, all the way down to 400 nanometers in the deep violet, which is the shortest wavelength that the human eye can see. A nanometer, to remind you, is 1 billionth of a meter. You may recall from the previous lecture, a wavelength of light is really tiny. This is the electromagnetic spectrum. But this is only visible light that I've shown. And indeed, light is just but one subset of a much larger entity called the electromagnetic spectrum. The electromagnetic spectrum is the sequence of photon energies that runs from the lowest energies to the highest energies. The lowest energy photons are over here on the right in this diagram. It's traditional to draw them blue to red, high to low. The lowest energy photons are long wavelength radio waves that can many times be many thousands of kilometers long. Very long wavelength radio waves are able to penetrate the oceans and are sometimes used to communicate with submarines under the water. AM radio, amplitude modulation radio, is down here at wavelengths between 1,000 and 100 meters. FM radio, it's more common these days than AM radio, frequency modulation radio, has sizes ranging between about 1 and a few meters. Shorter wavelengths include microwaves, the infrared, and this little tiny rainbow sliver is all the visible light that the human eye can see. Everything to the left is low energy, getting progressively, from the right, is low energy, getting progressively more energetic as we move to the left on this diagram. So radio waves, microwaves, and infrared are lower energy than visible light. When we break out into the visible light spectrum, we go from red light, orange, yellow, green, blue, indigo, and violet, light of increasing energy, decreasing wavelength. What's beyond violet? The ultraviolet, above the violet, which are very energetic photons. When we get past the ultraviolet, we get into extreme ultraviolet and eventually into soft and hard X-rays. And at very high energies, we get into the gamma rays. If I put on this same diagram, take away all the other labels, and show you the energies of some fairly familiar things. For example, FM radio at WOSU, around 97 megahertz every day. Wi-Fi, typical Wi-Fi system that you're using on your wireless laptop or tablet or even with your cell phone, has a frequency of about 5 gigahertz. That's out in the middle of microwave parts of the spectrum. If I had a thermal infrared camera, something that would allow me to see heat, like for example a thermal camera that someone would use going around a house looking for light or cold leaks, trying to beef up its insulation, would work here in the middle of the infrared. Here's visible light. UVA. This is the damaging ultraviolet radiation that comes from the sun. It's why we wear sunscreen when we go outside, so we don't damage ourselves and lead to a risk of skin cancer. But this is light which we cannot see. It's invisible to our eyes, but it most certainly carries energy, and that energy can actually damage skin cells. Medical X-rays are out here at X-ray wavelengths. Medical X-rays are photons of sufficiently high energy that they pass straight through the body. Dense parts of the body, like bones or heavy tissues, will absorb some of these X-rays. Light tissues and open spaces will allow the X-rays to pass through, and this allows us to make images of the inside of the human body. Gamma rays are very high energy. These can cause a tremendous amount of damage. For example, gamma rays come away from highly radioactive materials, make those materials quite dangerous. If a nuclear bomb goes off, you don't want to be anywhere nearby. If the flash and the boom doesn't get you in the overpressure wave, the gamma rays can actually throw enough energy through your body if they don't kill you outright. It can cause massive mutations that can make you extremely sick and often be fatal. And in bad cases, it might even turn you into the Incredible Hulk. The rate at which a light source emits energy is called its luminosity. This is the wattage of a light source. This is a way of talking about the total amount of energy that comes out of a light source in the form of photons. For example, this little LED bulb here might have a rating of 10 watts. That is a statement about the total amount of luminous power, luminous energy per second pouring off of the source. A watt is a measure of energy per second. Specifically, it's 1 joule per second, a joule being a metric unit of energy. The sun is a very big source of light and produces an enormous amount of energy. The wattage of the sun is about 4 times 10 to the 26 watts, or about 400 trillion watts. The sun is a lot brighter in absolute energy output than a 10-watt light bulb. Luminosity is a measure of total energy output, energy per second pouring off the star. Luminosity is an intrinsic property of the light source. It is independent of distance. It is what the light source produces, whether that light bulb is sitting next to me or, like the sun, is sitting 150 million kilometers away at the center of our solar system. This is the total power, the total energy pouring off per second, luminosity. The second quantity we can use to quantify brightness is called the apparent brightness. The apparent brightness is defined as how bright a light source appears to be when viewed from a distance. Put in wattage terms, brightness is not wattage, but wattage per square meter. How much the wattage, the luminosity, has been spread out over some area. For example, the luminosity of the sun, the wattage right up front and in your face of the sun, is about 4 times 10 to the 26 watts. However, once we go 150 million kilometers away, 1 astronomical unit, the brightness of the sun is 1400 watts per square meter. It's this energy that warms the surface of our Earth. So while the sun is producing 4 times 10 to the 26 watts, 4 times 10 to 26 joules, every second of energy pouring off the sun, it goes off in all directions. But the Earth only catches a tiny fraction, and we drop from 400 trillion to 1400 pretty quickly. The bottom line here is brightness depends upon distance. This is the important distinction between luminosity and brightness. Luminosity is an intrinsic property. It's how bright the object really is, totally independent of its distance. The sun will be producing 400 trillion watts, whether it's 1 AU away or 1 billion AUs away. But the brightness of the sun will depend upon whether we're close to it or far away. The sun appears a lot brighter in the star to Mercury and really faint and feeble as far away as Pluto. The relationship between brightness and luminosity is in terms of what is called an inverse square law of brightness. We've seen inverse square laws before. We saw the inverse square law of gravitation, that the gravitational force falls off as 1 over the distance squared. The same thing is occurring in the law of brightness. The apparent brightness of an object, B, is equal to its luminosity, L, divided by 4 pi times the distance from the source squared. So L is the luminosity in units of watts. D is the distance in meters. Because it appears as distance squared, indeed 4 pi d squared, is the surface area of a sphere of radius d. We have watts per square meter, and so we have brightness, apparent brightness, in units of watts per square meter when I express them conventionally in terms of metric units. This inverse square law of brightness is extremely important in astronomy because it gives us a way to measure the luminosity of an object that's very far away, because I can measure its apparent brightness, how bright the object, the star, the galaxy, the planet appears to be in my telescope here on the Earth, and I need to know how far away is it. So if I see an object of a certain brightness, is it really high luminosity but very far away, or really low luminosity, a dim object, very, very close? This inverse square law of brightness we're going to be using over and over again. Let's give an example of how the inverse square law of brightness works for a simple light source. For example, how bright does a light bulb appear to be? For example, I've got my little 10-watt light bulb here from the previous slide, and I'm sitting some distance d away. And I ask this classical statue here, hey classical statue, how bright is that light bulb? Classical statue says, it's B. Okay, now I move the light bulb 2 times further away, so it's now 2d apart. Okay, how bright is the light source? Brightness decreases as 1 over distance squared, so the brightness should be 1 over 2 squared, or 1/4. And so classical statue says, oh, it's now 1/4 as bright when I'm 2 times further away. In short, if the light source is 2 times further away, it will appear 4 times fainter. Finally, classical statue moves really close to the light bulb. Now it's closed up to 1/3 of the original distance. How bright does it appear now? Well, brightness goes like 1 over distance squared, but I'm now 1 over 1/3 squared, which is 1 over 1/9. Bring the 9 to the top. That's 9 times brighter. So if I go from comfortable reading distance to light bulb in my face, the light bulb appears brighter. In words, if the source is 3 times closer, it appears 3 squared, or 9 times brighter. We kind of all know this instinctively. Like when you were growing up and reading a book and you were far away from a lamp, and your mom said, you should get closer to the light. You try to read that book with the light too faint, you're going to go blind. Or that's what my mom said anyway. It's kind of hard to do that these days with tablets because they're self-luminous, but if you want to read a book, a conventional paper book, by a light at night, it's better off to be sitting next to the light than far away from the light. How fast does the light that you get from a light bulb get fainter as you move away? As 1 over the distance squared. This is a very important principle. This inverse square law of brightness we're going to see used over and over again in astronomy, and in particular in this unit, pay close attention to it because it's how one of the principal ways we're going to use to measure important properties of stars.